Hello, welcome back. Sorry, my pen was dead, so I had to recharge it and plug it back in here. So again, we're working on learning plan 1, load tracing. I'm doing example problem 4.6 on page 222. And the first question they want us to answer is is the equivalent horizontally projected load on the rafters. So I'm just going to do brief and short. So as you're watching this video, may help that you look at your textbook at the same time. So if you look here, I kind of attached the pictures in this whiteboard here to help you. So here we have our roofs or our rafters. Okay, we have a 512 pitch. Okay, so and if we go down to this aisle, here's our rafter. It's a 512 pitch, and they are 16 inches on center. So the first thing you want to do, is we're going to draw a free body diagram. So instead of drawing it at an angle, so this is why, and I'll explain why this is. So we have our rafter. Okay. We have our reaction here. So what you want to do when you're doing this, so you want to call this the reaction at the ridge, right? Because this is this point right there, and this is the reaction exterior wall. Okay, you want to orientate yourself so you're not confusing yourself. So the reaction ridge, and then this is the reaction exterior wall. Okay, now we got to figure out what is our load. So what I'm going to do is I'm just going to erase this because I need a little more room above this. Okay. So again, this is question 1. We're determining the equivalent load on the rafters. Okay, so when you read the problem, we got to figure out what's the load on the rafters. So if you look here, we got to figure out the load on the rafter. So we got roofing is 5 PSF. If I look on page 222, sheathing is 3 PSF. Rafters are 2 PSF and ceiling is 2 PSF. So those are dead loads. Okay, so we have our dead load, and that equals 5 PSF plus 3 PSF plus 2 PSF, and that's pounds per square foot, plus 2 PSF. So that equals, so our dead load is 5 plus 3 is 8, plus 2 is 10, plus 2 is 12. So we have a total dead load of 12 pounds per square foot on top of the roof. So remember, tops of roof and floors are loads per square foot, okay? All right, so now we got to look at our live load conditions. So we have walls, we're not in a wall, sobering, flooring, subfloor, joists, live load, occupancy. So the live load is not on the roof, but we have a snow load of 25 PSF. So live load equals 25 PSF. Okay, all right. So what we need to do is finishing my free body diagram here. So we know our rafter span between the ridge board and the exterior wall is 14 feet. Okay, so let's talk about some things. So here is my rafter. Okay. It's at a 512 pitch. Okay, and then basically the dead loads, so let me, just so it's clear here, the dead loads actually act along the rafter, okay, at the angle of a 512 slope. Okay, so we have 12 PSF. Okay, now we have a snow load. The snow load always acts horizontally. Okay, it does not act along the roof. So this is how structural engineering is done. Okay, so now I have two loads. Okay, now the question is, I want to convert that 12 PSF or this rafter into, so I don't have to do any trigonometry. Okay, if I make a right triangle here, I want to convert this 12 PSF and convert it so it's a horizontally projected. That's what they mean by that. So when you look at this, this is a right triangle. So would you agree that the hypotenuse of this right triangle, the length of the rafter, is longer than the horizontal projection? So if I kind of do this, this is mimicking my free body diagram. So this is 14 feet, but we know this is longer. Okay, so what you need to do, because we know this is a 512 pitch, we need to figure out, we want to take this load and we want to squish it so we horizontally project it down to the horizontal. So we're not doing math and trigonometry. So how do we do that? So that is only with the dead load. We leave the snow load alone. So how do we do that? So basically what you're going to do is we know we have a slope triangle here, right? We use the Pythagorean theorem and solve the hypotenuse, which is 13. Okay? And then what you're going to do is you're going to take 13 divided by 12. Okay? So you take the hypotenuse and divide it by 12, and let's try that again, is 1.08. So basically the load going from the rafter length greater than 14 feet down to horizontally to a rafter length of 14 feet, the concentrated point, or not the concentrated load, but the distributed load is 1.08 times greater than 12 PSF. Okay, so the key is take the slope divided by the slope of the slope triangle divided by the horizontal, and then we multiply it by times 1.08. Okay, so now we can do our loads. So now we got to figure out the distributed load, the total. We got to figure out our line load, our W, on top of this rafter. Okay, so remember that's a uniform distributed line load, W rafter. Okay, so remember how we find that. We take our load on our roof, pounds per square foot, and take it times the tributary width. So if we know, they're saying, oops, not doing that. If you look here, they're saying our rafters are 16 inches on center. So would you agree our tributary width is 16 inches, but we want to convert that into feet. So basically half 8 inches is going on one rafter and 8 inches is going on the other rafter. So the total load is, or total tributary width is 16 inches. Okay, so we go W equals, so we know we have 12 pounds per square foot times 16 inches is 1.3 3 feet plus the snow load is already horizontal, 25 pounds per square foot times our rafter spacing, number tributary width, 1.33 feet. We get pounds per foot. So our line load, uniform line load on top of the rafter, horizontally projected is, I'm going to say rafter. So if I reduce this math, equals, so we take 12 times 1.33. Oops, I forgot to add. Okay, so times 1.08. So I'm going to erase this because I want to make sure it's clear of how this works. So I forgot to take the multiplier of 1.03. 12 pounds per square foot times my rafter spacing times 1.33 feet times 1.08. That's my conversion factor to get it from the rafter length down to the span length, time plus 25 pounds per square foot times my rafter spacing. Okay, there we go. So that'll be my load on the rafter. So 12 times 1.3, whoops, 12 times 1.33 times 1.08 equals plus 25 times 1.33, and I get 50.48 pounds per linear foot. Okay, so question is rounding. So 50.48, the book gives you 50.6, depending on where you round it. So just to stay consistent with the book, what I would do is I'd round that up to 51 pounds per foot, but just to help, so we're going to say 50.6 pounds per foot. Okay, do we answer number one? Determine the equivalently horizontally projected load on the rafters. 50.6 pounds per foot. That is your answer to number one. So now we know the line load on top of that rafter when we do our calculation is 50.6 pounds per foot to design that rafter. Okay. Now it says number two. Okay, so that's the answer to question one. Okay. All right. Question two says determine the load per foot on the bearing walls. Okay. So the bearing walls are the exterior walls. Okay. So with that, so here's the ridge board, here's the exterior wall. So load per foot on the bearing wall. So basically what we need to do is we need to calculate the reaction that rafter. So basically what this is, this point load is we're going to take this, calculate this reaction right there at the ridge and this reaction right here at the exterior wall. That number, so there's a rafter every 16 inches, so there's a point load every 16 inches on top of that bearing wall. Because this is symmetrical, we only have to do one side. Okay, so you see that, right? 14 feet, 14 feet. So our span has not changed. So yes, I know it's confusing because the rafter length is longer than this horizontal span, but that's why this 1.08 factor comes in. It takes this and turns it horizontal, and it counts for that. So we're not doing angled math, angled trigonometry. Okay, so question 2 is determine load per foot on bearing wall. So I'm looking for bearing. That's why I'm going to leave a little room here. Oops, sorry. Load per foot on bearing wall. Okay. So what we're going to do is, so we figured this out. So basically, I did not need to show you this, but you'll need this anyway. So this answers question 1. Okay. You take your dead load that's along the rafter. You take it to the convert the load, do the conversion, and add your live load, which is a snow load, which is always horizontal, and you figure that out. So now to start loading 2, we know I'm going to draw this free body diagram, which I did. So the reaction at X, and that is every 16 inches, because there's a point load every 16 inches, per 16 inches. Okay, so now I need to solve for the reactions. So let me scoot this up. Looking at that free body diagram, okay, so I'm going to show you a shortcut. As long as this line load is uniform, which means it's a rectangle, I can show you how to solve these. Reaction ridge equals the reaction, that's a point load, exterior wall, or the bearing wall, right? This is bearing wall. Because remember, it's important to understand what side you're working on, which equals my line load times the length of my beam, which is my rafter, my span, divided by 2. So that equals 50.6 pounds per foot. And I multiply that times 14 feet. So now I'm my units are in pounds, and I divided by 2, and that equals 50.6 times 14 equals 708 divided by 2 equals 354.2 pounds. And your book rounds it down. Okay, per a point load. So that is a point load because this is a vector, a point load vector. This is not a line load. Every 16 inches, there's a point load. So another way to look at this, to solve these, would you agree that, because this is uniform, would you agree half of the load is supported by the ridge, and then the other half of the load is supported by the exterior wall? So 7 feet goes to the exterior wall, 7 feet goes to the ridge. So if I take 50.6 times 7, I get 354.2 or 354. Same way, but this is a shortcut formula to help you. Okay, so that means there's a point load of 354 pounds every 16 inches. Okay, however, okay, we need to get that. So instead of looking at, so if I'm looking at my wall, each of these vectors, force vectors, is a rafter, and each of these equals 354 pounds. But if the spacing is less than 2 feet on center, okay, we can convert into uniform distributed load by dividing spacing. Okay, so what does that mean? Because the distance, I'm just going to scroll up a little bit here. Because my distance, right, there is a point load every 16 inches. This is 16 inches. Sorry, I'm trying to grab that pen so it's legible. So basically what we can do, we need to find the load per foot. So the line load per foot on the bearing wall. So top of bearing wall. That equals 354 pounds divided by my spacing, which is 16 inches on center, 1.33 feet. See, now I get pounds per foot. Remember, the units on this distributed line load has to be pounds per foot. Pounds per foot. Right now, it's a point load every 16 inches along the top of that wall, because that's where your rafters are sitting. And that equals 354 divided by 1.33, and that equals 266.16, and your book leaves it at 266 pounds per foot. Okay, and that is top of bearing wall. All right, so I'm going to box that. So that is the answer to number 2. Okay, so we now, if you look here, we have our loads transferred from the rafters down to the top of the bearing walls and to the top of the ridge beam. Okay? Because the ridge beam supports the other end. So that's where we are. That's where we are with the load trace. Remember, you got to work top to bottom. Okay? Because we got to add all this up. So that was number 2. Now the question is number 3. Okay. Number 3. Determine so sometimes I'll be going back and forth to the to these diagrams here. Determine load on ridge beam. Okay. All right. So if we look here, this is uniform. So I have a reaction here, and another reaction, and a reaction. So this reaction of 354 pounds, if I draw that in here, so I may have to erase some. So that's the right side rafter, and then I also have another one, right? Because they're uniform. So basically, every 16 inches, I have 2 point loads because there's 2 rafters, this side and this side. So I got to take that point load and multiply times 2 every 16 inches. That is what's the load on that ridge beam because there's 2 rafters. This only accounts for 1 rafter on that ridge board, but there's 2 because you have the other side. Okay, so if this was a different span length, you'd add this reaction plus that reaction, and that would be the total load on that ridge board, ridge beam. They call it ridge beam, I call it a ridge board. Okay, so knowing that, so you can take 266 pounds per foot, right? Because this 266 pounds per foot is on top of the bearing wall and also on top of the ridge board. Because, okay, the reactions are the same on each side. And I multiply that times 2, and then I'll get 532 pounds per foot. Oops. 32 pounds per foot. Okay, that equals my line load on ridge beam. So the key to these problems is to keep yourself organized because you're going to be looking at these numbers at a later time because you'll need them. This will be the same as taking 354 plus 354, sorry. So every 16 inches, there's 354 times 2, 708 pounds of point load on that ridge board. And then I divide that by my spacing, and I should get the same answer. 532 pounds per foot. Same thing. PLF means pounds per linear foot. So, again, 350, let's see, let me go to the highlight. So we have 354, 354, 354 over here, and another 54. So we have a total of 708 pounds point load on that ridge board because there's 2 rafters. Okay. All right, so we answered number 3. All right. Number 4, determine the column loads. All right, so determine the column loads. So let me scroll down here. So let's look at this floor plan here. Column loads. So we have a column here, we have a column here, and we have a column there. Okay, so the column, so let me do a little bit of erasing here. All right, so it's clear again. So we only have columns in the interior of this building. So the columns, okay? So now you got to determine, so right here, this is where we're looking. Now you got to determine what's holding up, the columns are holding up the ridge beam. Would you agree? So that means we have to determine the reactions on the ridge beam. So those supports, this is the key. There is a support right here, there is a support right there, and there is a support right there underneath that ridge beam. So that means that's where my reaction points are where the columns. So let's draw that free body diagram. So 4. column loads. So this is the answer to number 3. All right, so zoom up here. All right, let's draw our ridge beam. Give yourself plenty of room. Isn't it nice to have engineering paper? So now we want to say south, north, center. Okay? Because we want to orientate yourself that we make sure we put the load in the right spot. So we're going to call this the south end. We're going to call this the north end of the ridge beam. So now we have a reaction south. We have a reaction. That's the or I'm sorry. Let's do this a little bit differently. Reaction sorry, reaction south column, reaction north column, and then we also have the center column. Reaction center column. So that reaction, remember, it just turns up, so the column is holding that load from the reaction. All right, let's get our line load on there. We calculated that from problem 3. So we converted that into a pounds per foot. So W ridge, beam equals 532 pounds per foot. All right, now we need distances. So let's put our distances on here. So we know this is 16 feet, and we know this is 16 feet. All right. So I'm going to make this easy for you. Let's take a look at this using tributary areas. Okay, it's going to go to the highlighters. So I'll do red. So if I look at this, because this is a uniform load all the way across that beam, would you agree 8 feet of that load goes to the south column, 8 feet goes to the north column, so, and then 16 feet, because 8 plus 8 is held up by the center column. So if you look at that, so we have, okay, that's the right column. Let's do different colors here. This much of the load is held by the north column. Okay, and let's see here, let's do blue. So, and all of this load, this area of the beam is held up by the center column. And we know that's 16 feet because we go 8, another 8 is 16 plus 8 plus 8. So to solve these, it makes life easier. So the reaction of south column, or the load on the, so the reaction is the load. South column, Would you agree equals the load on the north column? Because the tributary length here is the same. It's 8 feet on both sides equals the reaction, oops, of the north column. And that equals, so we take 532 pounds per foot, and then I multiply that times 8 feet, and I get a point load on the column. That makes sense, right? I don't, and that equals, so 532 times 8, 4,256 pounds. Okay. Now the reaction, or the load on the center column, equals 532 pounds per foot times, now my tributary length is 16 feet because I have 8 on this side and 8 on that side. So it's basically double that load. So 532 times 16 equals 8512. So this is the answer for number 4. So we have two columns that have to hold up 4,256 pounds, and we have one column that has to hold 8,512 pounds. Okay, so when you go into sizing columns, you're going to choose the column that has the biggest load. So that answer is number 4. So now where are we? So we got to, so we have the ridge beam, and then we went from the ridge beam down to, now we're on the only on the center. We didn't get to the down to the we're not on the exterior walls. Now we're down to the top of the floor beam. So we got from the roof. So we calculate. So the roof is held up by the ridge board, and then the ridge beam, and then the columns hold the ridge beam, and now we're down to the floor beam. Okay, so we still have to get the walls down to the top of the foundation wall yet. Okay, so what I'm going to do, I'm just going to take a quick break, and then I'll be right back. Okay, as soon as I figure out how to pause it. All right, welcome back. So let's continue on with our problem here. So we are number 4. So we figured out the column loads. So we have 4,256 on each of these exterior columns, and then we have 8,512 pounds on this center column. So that's answering number 4. So we have our loads. So the rafters are supported by the ridge beam. We got the loads per foot on the ridge beam, and then each of these 3 columns has to support the loads from the rafters. And then we have the load per foot on top of the wall on each of the bearing walls here. So that's where we're at. So now, question 5, determine the minimum width of the continuous foundation. Question 5. Minimum width of the continuous foundation. So if I go to scroll down here, continuous foundation. All right, so we're gonna have to go through a couple steps to get there. All right, so if you look, this is a continuous wall footing, and if you go down one more over here, the columns are supported by column footings, and then this is the floor beam here, and they also, so they didn't really, until you look at this, they added extra column footings in between the columns to support the floor beam. Okay, so that means, so if we need to, basically, if I look at this picture, oops, if I look at this picture, So this one kind of shows it really nice. This is the wall, the floor to the wall. So you can see half of the floor, this exterior wall is sitting on top of that concrete wall. So let's go back up to, so we need to get down to, where do we need to get to? Continuous footing. So we need to get to there and to there. So that means we got to transfer that load from the top of the wall down to the footing, and we got half of these floor joists are sitting there too. All right. So with that, let's start that. So load on top of the wall. So this is why you kind of need to bearing wall. And it's symmetrical, so the load on top of the wall is the same as the load is on top of the walls here. So that means the load, because these walls are symmetrical, that means the load will be the same on this one versus that one. So we need to go, where do we leave off on this side? We left at the load per foot on top of the bearing wall, which is 266 pounds per foot. Okay, so let's go to question 5 is determine minimum width of continuous foundation. Minimum width of continuous footings. Foundation footings, continuous footings, wall footings, interchangeable terms. Okay. All right. So we have our bearing wall. Let's see. We need to look at. So I'm just going to draw a plan view here. So this is our bearing wall. Okay. So remember that is, as soon as I find my cursor here, that is this guy right here and this guy. Okay. We know on top of that wall, we have our line load from the rafters of 266 pounds per foot. Okay. And we know the wall is how high is that wall? 7'6". Okay. 7'6" or 7.5 feet. Okay. So in your book on page 222, it says the walls, that probably includes the insulation, the studs, the drywall, it weighs 7 pounds per square foot. Okay, so if I look at this, I'm actually going to do this. Make this yellow. Okay. I know the walls on a 7 PSF. Okay. Sorry. Right there. So every square foot of height of wall weighs 7 pounds per square foot. So basically what we need to do is turn that pounds per square foot and turn it into a line load to get to the distributed load on the bottom of the wall. Okay. So we need to find the line load, uniform distributed load on bottom of wall. Okay. So to do that, we take 7 pounds per square foot times the height of my wall, which is 7.5 feet, and I get pounds per foot. Okay. So 7 times 7.5, and that's 52.5. And let's see, so I stay consistent with the book here. Floor joist, let's see here. I don't see it. Where's the wall? Yes, 52.5 pounds. So they're keeping it, they round it. So it's okay to round your numbers up when you're designing, because as long as you round your loads up, not too much where you're conservative, you're better off. Okay. So now we know we have 266 pounds per foot. Okay. On top of the wall, then plus the weight of wall, we're going to add those two together. So we have 266 pounds per foot plus 52.5 pounds per foot equals 266 plus 52.5, and I get 318.5 pounds per foot. Okay, so now what do we have? We have our wall. So our line load on top of this and the top of this is 318.5 pounds per foot. So now we just have moved the loads down here and down here. So now we're at the floor level. Okay, so as you notice, we got to keep adding the loads up. We're continually adding the loads. Okay, so we're still on problem 5. All right, so now we have the floor. We got to get the floor. We got to get these loads. We got half over here, half over here, half over here, half over here. We got the floor loads. That's the flat floor load. So we got to calculate the load per floor joist. So we got to figure out what are our floor joists, what's their spacing of our floor joists to figure out our tributary width. Okay, so let's see if it's in this diagram. Floor joists, rafters. Let's see here. Floor joists are also 16 inches on center, and they have a 14-foot span. Okay, so I'm looking down there. All right, so let's do the free body diagram of the floor joist. So step 5, I'm going to say call this part A. Part B, let's look at our floor joist now, because we're not to the top of our foundation wall yet. Okay, so this is a joist. Okay, I'd have to say, so we have a reaction here, and that is our wall. And then we have a reaction here. Would you say, looking at this diagram, we have a floor beam. See, one end of the joist is supported by the floor beam, one end of the joist is supported by the foundation wall. Okay, so this helps you stay orientated. So I'm going to say floor beam. Okay. All right, so we need to go find our line load for the joist. So looking in your book, we need to find the dead load and the live load. So we need to find our dead loads. So soil bearing flooring is 2 psf. That's the weight of the sheeting, floor sheeting. Plus subfloor is 5 psf. I'm finding these on page 222. It's giving us the problem. Joists are 4 pounds per square foot. Okay. live load. Okay, now we don't have to do any horizontally equivalent loads because it's already horizontal. Live load, snow load, walls, and then the rafter we already have. All right, so we can, our dead load is 2 plus, that's 11 PSF, and then our live load is the occupancy load, which is 40 PSF. So now we can take 51 PSF times our tributary width. The joists are 1.3 feet on center, and that equals 51 times 1.33. Let's double check this number. 51 times 0.33. And that's 67.8. So let's see what your book, how your book answered that. I'm looking for the floor joist number here. And floor joists, we have, they're rounding it to 68. Okay, I always like to round up to an even number. I just doing this just to help you so you can follow along in the book. Pounds per foot. So this equals 68 pounds per foot. And that's that line load, uniform distributed line load. All right, so to solve for reactions, our span is 14 feet. So we know half goes on the floor beam and half goes on the exterior concrete wall. So we're going to take the reaction floor beam equals the reaction of the concrete wall, which equals 68 pounds per foot times, so each one is holding 7 feet of length. Remember, if I just divide this in half, half is going this way, half is going the other way, times 7 feet, and that equals 68 times 7, 476 pounds, 476 pounds every 16 inches. That's a point load, right? Because if you look at my units, pounds per foot times feet, it turns into pounds. So there is a point load on that wall, 476 pounds. And then on the floor beam, 476 pounds. Okay, so now we got our point load. Okay, so now we got to convert that into a line load. Remember, less than 2 feet on center, we can convert that into a line load. So we want to keep this so we kind of know. So now we're going to take 476 pounds per foot and divided by 1.33 feet, and that, oh, I'm sorry, this is a point load. That's each rafter sitting on that wall. So let's do that again. 476 pounds every 16 inches. So if I divide by 1.33 feet, I get 357.8, so 358 pounds per foot on, okay, on the wall. On wall and on joist, per joist. So remember, per joist, okay? So now we know, now what did we just find? We know we just added the weight of the joist onto here. So now we can add the weight of the wall, the rafters, plus the wall, plus the floor joist to get our load per foot on top of that wall. Okay, so you got to add it up. So don't forget about that. So this is part B. Okay, so part C, our load per foot, top of continuous footing, top of foundation wall for the continuous side. Number the two exterior walls. Continuous top of foundation equals. So we got to add 318.5 pounds per foot plus what's the load on the wall from the floor joist. It's 400, whoops, that's 358 pounds per foot. Okay. And that equals 318.5 plus 358, 676.5. And I would round that up to 6. What would I round that up to? See what 6, they keep it at 675.5. 676.5. All right. Let's see. Okay. I'm just going to go to 676. 676 pounds per foot. As I remember, this is the line load from the bottom of the wall plus the line load from the joist, the uniform from the joist, will equal W top of foundation wall. So you got to kind of keep track of what was included in that calculation, what wasn't. So you got to keep bringing the loads down. Okay. So when I design my continuous footing, this is the number I'm going to use. Okay. Now, the question is, we're still not done yet because the question is asking what's the size, determine the minimum width of the continuous foundation. All right. So based on code, you're going to look in your code books. You're going to determine the width of your foundation, and then we gotta that's kind of a given. That's based on soil types and stuff like that. So if I look here, I just gotta go. They give you kind of dimensions of our concrete wall here. Okay, I know my concrete stem wall is 2 feet. So if I look right here, so I'm gonna kind of jump down on this diagram here. Okay, so this is my 676 pounds per linear foot. Okay, now I got to add the weight. If you look here, I got to add the weight of the concrete on a pounds per linear foot. Okay, so I know it's 8 inches wide by 2 feet deep. Okay, so 8 inches wide. So right here, that turns into feet. And concrete, we typically weigh 150 pounds per cubic foot is an average unit weight of concrete, and it includes reinforcement. So that's the footing. So let me use a highlighter here. So if I look at my stem wall, this is what's doing the calculation. 8 feet, 8 inches wide by 2 feet high times 150 will give me the weight of that stem wall to get down to the top of the footing. Okay. So this is part D. So we know weight. I'm going to say W stem wall. Okay. That equals 8 divided by 12 feet times 2 feet is the height. And concrete weighs, the unit weight is pounds per cubic foot. Pounds per cubic foot. Cubed foot. That's reinforced concrete. So feet times feet, I'm left with pounds per foot, and that's what we need. Okay. So 8 divided by 12 times 2 times 150, and I get 200 pounds per foot. That's how much that concrete wall weighs. 200 pounds per foot. Now, okay, W, now I gotta, so E, W, my line load, I just say W, top of footing. So now we know this is the top of the foundation wall is right here. We gotta add the weight of the stem wall to get the total load on the top of our footing. Okay. So with that, so we have W line load top of foundation plus the line load from stem wall, and that equals 675.5. I'll just do that to go back to the book. It's consistent with the book. Plus 200 pounds per foot. And that equals 875.5 pounds per foot. So that is my weight on the top of my footing. Okay. All right, we're still not done yet. That is finally the weight. All right. Now we can size the footing. Okay. So based on codes and stuff, as you can look here, it looks like if we look here, they assumed a footing thickness of 8 inches. Okay, so what we're trying to find is the width of that, because the thickness of 8 inches. So if I take 8 inches times 150 pounds per cubic foot, that concrete weighs 100 pounds per square feet. That should actually be a square feet. Okay. All right. So how do I do this? So how to determine the width of the footing actually is depending on the soil bearing pressure. And me as a geotechnical engineer, this number right there is the number I need from you as an architect to determine what kind of foundation I need and how wide I need to make my footing. So if we look back at our problem, it says soil bearing pressure of 2,000 pounds per cubic foot. So Q, I'm going to call that Q, equals soil bearing pressure, and that equals 2,000 pounds per square foot, because pressure is a force over an area. So that's how much that soil it can hold before it starts settling and your foundations start cracking. Okay, so we have something called Q net. So it's a lot of times what they call this, okay, or Q net, we got to subtract the weight of that thickness of the footing. So we're going to take 2,000 pounds per square foot minus the thickness of my footing, because that's typically designed flexually strength. It's typically, we know this, it's just the width is for the soil mechanics reason. So minus 8 divided by 12, because it's 8 inches thick, times 150. So this is feet, this is pounds per cubic foot. So this is pounds per square foot. Ends up, so 0.67 times 150 equals, we're just going to say 100. So this equals 100. So my Q net equals 1,900 pounds per square foot. Okay, that's what my soil can hold, the pressure. All right, so now knowing that, we know Q net equals my load divided by my area. And this load is in pounds per linear foot, because what we're going to do is we're going to base it on a per foot basis. We're going to assume that we're cutting that foundation and we're just looking at 1 foot long piece of foundation. So instead of 875 pounds, 0.5 pounds per foot, we're going to say, it's basically saying every foot there's 875.5 pounds on that foundation. So we can kind of think of that way. Divided by area. Okay, so we need to solve for area on a per foot basis. Okay, so to solve for that, we're going to take, doing algebra, basically these switch places. We go P over Q net, and that equals area. So we have 875.5 pounds divided by 1,900 pounds per square foot, because remember, we're doing this on a per foot basis. We're just taking out, we're designing basically a 1 foot long foundation per foot basis. Otherwise, the units don't work out, because see, the pounds cancel out. Now we're left with area. Remember, area is a length times a width, so that's a square feet. We need square feet. So we get 875.5 divided by 1900, and I get 0.46 square feet. Okay, so we know it's on a per foot basis, so X, my width, this equals width, times 1 foot length equals my area. Okay, so that means we take area divided by 1 equals my width. And that equals 0.46 square feet. So this is a foot here, divided by 1 foot. So my width equals 0.46 feet. So if I take that times 12, so that's only a 5.5 inch wide footing. Does that meet code? Inches wide. Does that meet code? No. Obviously, your footing cannot be narrower than your foundation wall. Your foundation wall is 8 inches wide. Plus, I do believe code has, your footing has to be at least 4 inches wider on each side of your foundation wall. So we're going to round that up to what? So 8 inches plus 4 plus 4. Your footing is going to be 16 inches wide. But according to my soil mechanics, my building will be okay underneath this load. A 5.5 inches wide footing will work, but its constructability doesn't happen. All right, so this is the answer to number 5. Minimum width, 16 inches. Okay, all right, last problem. We're getting there. Determine the size of the interior footings. Okay, number 6. Interior footings. All right, so let's take a look at this drawing. So we previously, as remember, we calculated column loads. We calculated this column load and that column load, okay? Now we have a floor beam. So, and then you got to remember these column loads actually transferred through and go right onto the top of the foundation wall. So this is typically where you'll see a pilaster in your foundation wall where that bump out that'll create it kind of like as a mini column. So now we got to figure out, we got to transfer the column loads down here, and we got to transfer the floor beam loads onto these columns. Okay, so basically these columns support the floor beam, so we need to get the load on the floor beam. Okay, so with that, let's draw our floor beam. Whoops. Okay, floor beam. So looking at the diagrams here, how long is this sucker? That's a good question. Well, it's 16 plus 16, right? 32 feet. Do you agree? Because when we can determine that by one of these diagrams, wherever it is. Yeah, right here. So here's this yellow here is my floor beam. So it's 16, and the center column is 16 feet in, and then it looks like they divided the span between the center column to the wall by half. So that's 8 feet in between. Okay. So with that, we can draw our free body diagram. Remember, the reactions are where our supports. That's what they are. So we can do this. Okay. So we can call this our north wall. Okay, this is our south wall. All right, so I didn't quite draw that right yet. Oops. Okay, so we have one in the middle here. So this is the reaction center. And then we have these little guys, these extra ones. R, R. Okay. All right, distances. You can identify these. Basically, you want to orientate things. All right. So if I just draw, so we have 8 feet, 8 feet, 8 feet, 8 feet. So now we need to figure out the load on top of our floor beam. Okay, so this is a column, column, right? Interior columns. So by looking at this, which one do you think will actually have to hold most of the weight from the floor beam? Probably pretty much all the same. So these three will, so if I look at this just quickly, before I do this calculation, only half of this, so 4 feet of this comes to the outside wall, 4 feet of this comes to the outside wall, right? And then the rest of them have to hold 4 feet plus 4 feet, 4 feet plus 4 feet, and then so this column, the center column, and this column all hold the same weight from the floor beam. However, remember, don't forget we have, what do we have here? Don't forget we have 8,000 512 pounds from the column that has to transfer through, right? Remember this, 4256. And we have a point load here, 4256 pounds. So basically, principal transmissibility, you're just going to transfer that right down to the column, okay? And this is 4,256. All right. Okay. Because remember, you gotta get these loads add up. So where are we in the center column? So if I'm trying to find the diagrams here. So we got to the floor joists. Now we're sitting to the columns. So we got all the floor joists are add. Now we're at the floor beam, and then we need the floor beam down to here. We got this done and this done. So don't forget about these columns. Those point loads are transferring onto that floor beam. Okay, it's very important. So, and I'll show you a little trick to make your math easier so you don't have to do a bunch of moment equations. Okay, so with that, now we got to figure out our uniform distributed line load from the floor beam. So we need to look at the reaction, because when you look at this diagram, whichever one is here, we'll find it here. That one's, let's go up right here. Let's look, see, this is my floor beam here, right? So I need the reaction from this end of this joist plus the reaction from the end of that joist. So it's uniform. They're the same, the joists are the same length on each side of the floor beam. So all we have to do is double that reaction load. So we just got to find it up here. So this is where you need to keep track of here we go, right here. Our floor beam, our wall, right here. So this is the guy we need right here, 476 pounds every 16 inches. We convert it into a line load. So this is the value we need right here. So this is why it's important that you organize your work. So 358 pounds per foot times 2, because there's 2 floor joists on that floor beam. 358 pounds per foot times 2. 358 times 2, and it's 716 pounds per foot. So W equals 716 pounds per foot. All right. So now let's figure out these reactions. I'm going to call this column 1. I'm going to call this column 2. Our south wall, our center column, just so we know, and north wall. So now we're going to decide which one is going to carry most of the load. Okay, so a little discussion here. So we notice this point load, the center column is transferring down to this column footing in the middle here. Okay, so what do we do? So we need to figure out, so what I'm going to do here, so this center column is holding 8 feet of the floor beam load plus 8,512 pounds. Would you agree? This column is only holding 4 feet of, or I'm sorry, 8 feet of the beam load. So this one's smaller than that guy. And then the north wall is only holding 4 feet plus the column load. So I'd say your center column is going to carry the largest load by looking at this diagram. Okay. So with that, let's calculate that. So we're going to take the reaction at center column equals 716 pounds per foot. I'm going to multiply that. So 4 feet here and 4 feet on this side. So that's times 8 feet plus 8,512 pounds. And that'll be my reaction in the center. Okay? So basically what I do for practice, solve each of these reactions because they're column footings, right? But you're only in that column footing, you're only going to design one of them, the one that has the largest load, typically. So 716. Okay. 716 times 8 plus 8,512. So 14,240 pounds. Okay. All right. So with that, okay, 14,240 pounds. Just going to double check. All right, so the floor beam, I'm just looking at making sure my answers are correct. I didn't make a math error there. Nope, that looks about right. Okay, I'm just going to double check here. 716 divided, 716 pounds per foot times 8 feet plus 8,512, 14,240. So the book gets a little bit different answer, which is not a big deal. So maybe I made a math error somewhere, but that's why people check your work. They get 224. So they get 714. I get, oh, okay. I get 716, probably because I rounded up before. So it depends when you start rounding. It's okay to be higher than lower. Okay, so now that center footing, column footing, has 14,240 pounds on it. Okay, so that is this guy right there. So now we got a size. The question is asking, determine the size of the interior footings. I only need the size one. And it's good practice that you don't keep changing the size of your footings for construction. It actually you think you're saving money by saving material. You're not, because it takes longer to form up the work. So if you keep them all the same size, use the worst case scenario, it makes life easier. You'll actually save money. Okay. So we know, what else do we know? We know Q net because we already solved this, right? We're assuming a, 8-inch thick footing. Q net equals 1,900 pounds per square foot. This equals our P, so we need a square footing. So Q net equals P over A. We need to solve for A, so P over Q net, and that equals 14,240 pounds. So this is a number that I need as a geotech too. What's my maximum column load? Divided by 1,900 pounds per square foot. So we take that number, I'll just use my numbers, divided by 1900, 7.49 square feet. Okay. However, we know it's square, right? A equals x squared. We take the square root of A, square root of a box, then we can get the side of each side. And so we take the square root of both sides. and that equals the square root of 7.49 square feet. Take the square root, and I get 2.73 feet. Never, always go bigger, never go smaller. So 2.75 feet by 2.75 feet. Okay, and that equals, I'm going to say 2 foot 9 inches by 2 foot 9 inches. Okay, so you always want to round larger, so you cannot, basically what you cannot exceed the net bearing pressure of 1900. So by making the area bigger, if I look, this area got bigger, P divided by area, this will, my Q will be less than that number if you put the math in there. Okay. I do believe we solved all the problems the question was asked. So hopefully by me going through this and going through the diagrams, this basically the thought process on how to get through these problems. So what I want you to do is, go through this. You can work on problems starting on page 227 through 4.1 through 4.5, okay? And then you have the solutions in the solutions manual to help you get through these problems to see if you're on the right track. And then we will adjourn. We'll see you next time. Thank you.